Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, these days we are discussing the basics of plasma physics, which we will refer very frequently when we discuss the space environment effects. So, in the last session we discussed about the plasma, and we have seen the behavior of the external magnetic field on a moving charged particles, and we have seen that particle it gyrates about the magnetic field axis or about the flux lines of the magnetic fields, and we calculated the gyro radius, or it is also called the Larmor radius, as well as the cyclotron frequency. So, today we will continue with the same topic, but we will consider specially that is how this particle is guided in the magnetic field, and we will derive the expression for the guiding center, then the pitch and the pitch angle of the that is the helical trajectory, that already I told that the particle that moves in a helical trajectory. So, we will find the what is the pitch and the pitch angle of the helical trajectory, and then we will see that is what is the plasma when it creates the current, what is the property of that plasma material here. So, that also we will see, and then we will see what is the expression for the magnetic moment, and then we will see it is uniform magnetic as well as electric field we will see. So, it is a combination of both the magnetic and the electric field, and then we will see here there is a drift, and then we will see what is that the drift and the drift velocity. So, as I explained in the last class, that is the force on a moving charged particle, that is given by the Lorentz force. So, from the Lorentz force we write this the equation of the motion. This is the force, this is the acceleration multiplied the mass, which is equal to the force exerted by the magnetic field on the charge. And we assume that the particle is moving in a arbitrary, that is direction. So, we have taken the velocity components both x, y and z, but the magnetic field components we have considered only it is z directed. So, whatever is the component of this velocity which is directed along the z direction, we will call it the parallel velocity. So, this we will name also this is parallel. Then we derived this differential equation, this is the second order differential equations, and here the W that is the omega c, that we call it the cyclotron frequency, and this is the expression also we have seen how it was derived, and this is the independent of the velocity, this is independent of velocity, and RL is the Larmor radius, and that also you have seen the expression. This is given by the velocity. Velocity means the perpendicular component of the velocity divided by the cyclotron frequency. Here this component, that is the vertical component of the velocity, is Bx square by By square. In fact, this is the tangential component of the, that is the tangential velocity when it is gyrating in a circle, or it is doing a circular motion. And this is the period will be, that is the period for one gyration, this is twice pi by the cyclotron frequency. Then we have seen, since these two equations are the harmonic differential equation, so we found that, we wrote that there the solution we can write it in this form. So, both the Bx and By, and this Bx and By component we have written, we can find out if you put these values here, these two equation will be satisfied. And then the horizontal component of velocity, that is the parallel component of velocity, it is constant, because the magnetic field does not have any action, or it does not exert any force, or it does not change anything when it is the charge is moving along the direction of the magnetic field. So, this you were saying, so here the magnetic field is moving towards the paper. This symbol shows the magnetic field is this towards and the particle is moving in the xy plane. So, the particle is in fact, here since I am considering if the zx the z component if you do not consider, then it will have the circular motion. And for the, this is for the positive charge. If the charge is a positive charge, if you take a positive charge q, so that will move in a counterclockwise direction with the tangential velocity v t, like that. And for the electron, it will be the clockwise. And one more thing here, you have to see that the Larmor radius, their charges may be the same, but the Larmor radius is the different, because you can see from there the expression, you can see that is positive charge. If you take a proton, then it will have, or a ion will have the higher mass. So, it will have the higher the Larmor radius. Okay. So, this is one the positive, one is the brown and the negative black in the magnet, and we have considered this positive one is the positive ion and the other one is the electron. Now, this is our velocity components. Now, what we will do, we will take the integrate all those velocity components. If I integrate this velocity components, I will get its the position. So, I will integrate this from integrating equation 1 in the limit so integration of limit will take 0 to t. So, I will write it one expression. So, I will write the V x dt 0 to t. So, that will be V perpendicular. So, this is constant. So, I will integrate only this one 0 to t cos of omega c t plus psi. I will do first one and then the other one. So, what it will give me? It will give perpendicular component of velocity, then that is sine of the cyclotron frequency omega c t plus psi divided by omega c, and then we have to put the value 0 to t. And here in this side it will be it is 0 to t. So, it will be dx by dt and dt. So, then it will give me V. I can write it like this, B perpendicular by the cyclotron frequency omega c, then it is sine of omega c t plus psi minus sine of psi. Now, the right hand side I can write the left hand side. So, it will be x. So, at x t I will write x t, and then at x t at t is equal to 0 I will write it x 0. So, now this term, that is the perpendicular component of velocity divided by the cyclotron frequency, is the Larmor radius R L. So, I can write this as R L, then sine omega c t plus psi minus R L sin psi. Okay. Now, I can take this term on the other side. So, the x t I will get is equal to R L sin omega c t plus psi plus x 0 minus R L sin psi. Okay. And similarly, I can show, that is the y t also. Similarly, we can show y t is equal to minus R L, because here it is sin omega c t. So, when I integrate it, I will get minus sin. So, I will write it minus sin cos of omega c t plus psi, then plus y 0 plus r l cos of psi, and this will give the z will give, I will get a term z of t actually, I will get z of t is equal to z 0. So, it is at t is equal to 0, and then it is the b parallel. B parallel means this is the z component of the velocity multiplied by the time t. Okay. So, we can name this as our equation number 2. Okay. So, what are here the x 0, y 0 and z 0, they are the coordinates of the location of the particular t is equal to 0, as already I told. And what is psi, that also I told in the last class, this is the phase at t is equal to 0. Okay. So, now you see what is happening here. So, for what is if I see this the position x, y and z. So, this equation show that the particle moves in a circular orbit. So, since the equation you see the x and y equation, if you see the expression for x, expression for y. So, this represents a circle. If you this is the equation of a circle, means if I what I mean to say that if I do, so what I will do x t minus x 0 plus r l of sin psi. Okay. So, this if I do whole square plus y t minus y 0 minus r l cos psi square. So, this gives me the equation of this circle. So, what already you see this is the Larmor radius. So, where this is happening? This is happening in the perpendicular to the magnetic field line. So, it is happening in the x y plane, and here the angular frequency is omega c, and the radius is r l about the guiding center. And what is happening? So, this is the guiding center which has come from here, So, this is the guiding center. So, the guiding center, it simply moves linearly along z at a uniform speed. So, already you have seen. So, this is moving with a uniform the velocity of v parallel, and the particle motion is helical. So, here you see this is the guiding center, whatever I find, that is the x 0, y 0 and z 0. So, this is for a this is for an ion, positive ion, this is for the electron, and here again the magnetic field is going to the paper. So, you can see, so this is the guiding center and this is the magnetic field is gyrating in a helical path. So, next what we will next we will see that is what is that this helical path. So, what will be the property here? So, properties will be here the pitch angle, pitch and pitch angle. So, we will see how we can find it, pitch and pitch angle. Okay. So, just we will see what is pitch and what is pitch angle. So, you see, so this is actually our B parallel and this is B perpendicular. Okay. So, you see this is the helical path it is taking. So, what is the pitch actually? So, pitch is between the distance between the two turn. So, this is the two successive turns. So, P, and if I want to find what is the pitch angle, so I can find the pitch angle from, so the schematics shows here, if I know the circumference, and then and if I know the pitch, so I will be able to find the what is the helix and the what is the pitch as well as. So, you see what is pitch here. So, means one pitch. So, in one period for the or one the electron when it gyrates for one period, it moves one turn and it goes to the second turn. So, I can say that my P is equal to, so or I can write here pitch is equal to V parallel. So, it is in the along the axis of the helix, it is moving with the velocity of V parallel. So, I must multiply by V parallel with the that is the time So, I will get this is the pitch, this is the distance between these two turns. So, I can write now. So, what is the B parallel and T, I can write it twice pi by omega c. So, if you know the cyclotron frequency, that, or if you know the what is the parallel component of velocity, you can calculate the pitch. Now, how to calculate the pitch angle? So, in order to calculate the pitch angle, what we will do? So, here I can write that if this alpha will be equal to tan inverse pi d divided by p. So, I can write it tan inverse. So, it will become twice pi into R L and p will become V parallel twice pi by omega c. And this R L I can write tan inverse twice pi, that is B perpendicular divided by omega c. So, and this is becoming twice pi into V parallel omega c. So, finally, it becomes tan inverse B perpendicular to B parallel. So, this is the expression for the pitch angle. So, if you know these parameters like what is the cyclotron frequency, what is the Larmor radius, this the properties of the trajectory or the helical trajectory is you can find it out. Okay. Now, the other topic is diamagnetism. So, what is diamagnetism here? Now, you see whenever you just consider a positive charge is moving in this direction and a negative charge is moving in this direction. So, we consider the current direction is the direction of the positive charge. So, you see in the both case the current direction will be anti-clockwise. If you see this picture, in both the cases and if you see the right hand rule, then because of this current the magnetic field is coming out of the paper. But the external magnetic field, this is into the paper, but this will create a magnetic field which will come out of the paper by the the right hand rule. So, what does it mean? That whatever the current is being produced by the movement of this plasma particle, this is creating a magnetic field which is weakening the external magnetic field. So, this property is called the diamagnetism. Now, we will consider the case where both the electric field and the magnetic field are present. Okay. So, our previously we consider only magnetic field. Now, we will see that if we put both the electric field and the magnetic field, what is the effect on the charge, the movement of the charge. So, we will consider this figure. So, here you see what we are doing, we are considering that is a particle is moving. What we will do it like this, we will define the axis. So, we will define this as our y axis, this as x axis, and this will be our the z axis, means it is coming out of the paper. So, this is our z axis. So, here the magnetic field, it is coming out of the paper. So, we assume like that, since this dot is there, means it is coming out of the paper, and the electric field is in the y direction. So, it is in the y direction, electric field in the y direction, magnetic field is in the z direction, and you are assuming the particle is moving in the x direction. So, here this is the x direction, the particle is moving in the x direction. Now, let us see what will happen to this particle. Now, you see, now we are considering both the presence of the electric field as well as the magnetic field. So, the force on the particle is, now it is both electric as well as both components are there. Now, what this E will do? So, if the charge particle is moving along the electric field, it will accelerate it. If it is moving against or in the opposite direction, then it will deaccelerate it. Now, let us see what is happening here. So, in the absence of the electric field, this B cross B force would cause the particle to gyrate clockwise direction about the normal to the paper. So, it will become just it is a circular motion, but now because of the presence of the electric field, what will happen? So, when the suppose the particle is moving in the downwards like this direction, it is moving. So, when it is moving downwards, this electric field will deaccelerate it. Deaccelerate means its the radius, the Larmor radius will change. Now, as the B force redirects, means when it is going in this direction, so it will you will increase its velocity and it will increase its gyro radius. So, what is the net effect? Net effect is like that, in when it is charge is moving in the downward, its radius is getting changed or its velocity is changing, whereas it is coming in the upward direction or in the direction of the electric field, it gets accelerated and its radius changes. So, net effect is that it is as if it is stretched in the or it is drifted along the x direction. So, this is we have taken a particular case where we have considered both the E B and both the three like the particle is moving in the x direction, electric field in the y direction and the magnetic field in the z direction. So, this is the result. So, it is the net result is that the particle it drifts to the right. So, now we will see it in more in some more detail. So, what we will do here we will consider that we will not consider we will consider arbitrary direction of the electric field like we have considered previously. We will consider the even the velocity direction also, that is the direction of movement of the particle is also arbitrary. However, we will keep that that same that is our the same whatever we put the direction with the magnetic field, that is z directed. So, now we will write down the what is the force on it. So, here the now we will write down the what is the that is the equation of motion. So, this is d of or I will first let us write down these all the particles velocity and all these things, then we will go further. So, what we will do, we will first write the E and then we will write the. So, we will write the E field here as E perpendicular and then E parallel. So, E parallel means it is the parallel means parallel to the magnetic field. So, we will write E parallel to the so this is we are writing E field as a perpendicular component as well as the parallel component. Okay. And then we will take another assumption here we will take that is our that is it is previous the velocity we consider both x and y, but here we will consider only x direction without any loss of generality we can write it. So, this is further assumption and then this is parallel. Okay. And the v t this velocity will take as v perpendicular t and then the v parallel v parallel. These are all vector. Okay. So, now the Lorentz force equation or the equation of motion of the particle we can write here m d by t is equal to q, then x component of that is E t E parallel okay. and so two components. So, we have written for this component, and for this parallel component we will write it m v parallel dt will be equal to q e parallel. This component is 0 because this B parallel is the, so cross product will be 0. So, this part, so plus 0, since I am writing it V parallel cross Z. So, this will be 0. Okay. So, what this means? So, it means it is a constant acceleration along B. So, now we will write this equation for the perpendicular component d perpendicular by dt. So, this is equal to q x v perpendicular and our this B parallel by dt is equal to q e parallel z. So, this we write it suppose A. Now, this equation, it is a non-homogeneous equation here because of this term, So, the way we solved it previous case when the E was not there, it was straightforward, but now since this differential equation is not a homogeneous equation, we need to take a particular that is called, we will put as a solution, we will put two function, complementary function or a particular solution and a complementary solution, and we will proceed it into our next. So, further we will see how to the calculate what is the velocity and what is the trajectory of the particle in the next session. Okay, thank you very much.